Have you ever wondered how Kubernetes decides which pods can talk to each other? Or maybe you've heard about network policies but never really understood how they work or when to use them. In this video, we're going to answer those questions by building everything in a real Kubernetes cluster. We'll start with fundamentals, learn how Kubernetes network policies work, and then take a step further with Cilium. You'll see how to secure communication between applications, write DNS and HTTP-aware policies, and use Hubble to watch your network traffic in real time. So without further ado, let's get started. Let's start with this question: why network policies even matter? As you can see here in this picture, everything can talk to everything. Front-end pod can talk to the internet and also can talk to the database pod. It can be in the same namespace or other namespaces like data namespace, and that's the default behavior of Kubernetes. Let me show you a real example. We have a namespace called dev, and here we have some pods. Let me just show you. Get pods in the dev namespace. As you can see here, we have backend, database, frontend pod. Actually, these are simple applications that are written with Python to illustrate these concepts to you better. And also these applications have a UI that we can interact with them and send requests to the backend, the pods in the same namespace or other namespaces, or even the assets on the internet like Google or other APIs. And here, let me just test to send a request from front-end pod to the backend pod on 8081 port. And as you can see here, the front-end pod can communicate with backend pod on the 8081 port. And also let me just connect to the google.com, for example, from the Postgres pod. As you can see, it connected perfectly fine. And also we have Hubble UI that we can see that database pod can talk to the world. It means the internet that we, as I showed you, we could talk to google.com, for example, and also the front-end pod can talk to the database and backend pod. And at first glance, this might look perfectly fine. Our application is working, services can communicate, no errors. But from a security perspective, this should make you uncomfortable, because this is also the default networking model in Kubernetes. It means by default, Kubernetes networking is flat, and every pod can generally communicate with other pods in the cluster unless you explicitly restrict it. But why we do care so much about this communication? Let me just give you a scenario. Now imagine that an attacker exploits a vulnerability in the front-end application. Maybe it's a remote code execution vulnerability, maybe it's a vulnerable dependency, maybe someone accidentally exposed a debug endpoint. The attacker now has some code execution in the front-end pod. But what can they do next? They can try to reach the backend, they can probe internal services, they can scan ports, they can attempt to connect directly to the database. This is called lateral movement in the security. And in many Kubernetes cluster, nothing prevents it. Most applications don't actually need unrestricted communication. Let me ask you some questions. Does the front end really need direct access to the database? Probably not. Does the metric service need to talk to the payment service? Probably not. Should every pod allow to access external APIs on the internet? Definitely not. But what do we really want? We want front-end can communicate with backend and backend can communicate with database. But we don't want front-end connect to the database and also a random pod on other namespaces or in the same namespace can talk to the payment service. And only the communication that is explicitly required should be allowed. This is the idea behind zero trust networking inside Kubernetes. And this is exactly why network policies exist. They allow us to define who can talk to whom, on which port, in which direction, and with Cilium, even at the application layer. And that's it for this section. Before we start writing network policies, we need a quick mental model of three core concepts in Kubernetes: namespaces, pods, and services. Let's start with namespaces. Namespaces are a way to group resources inside a Kubernetes cluster. You think of them as a virtual cluster inside one physical cluster. For example, we could have production, staging, or even dev or monitoring namespaces. And in the context of network policies, namespaces often represent security boundaries, and we will later use them to control cross namespace communication. And pods. Pods are the smallest deployable units in Kubernetes, as you know. Your application runs inside pods, not directly on the nodes. When you scale an application, Kubernetes creates multiple pods, each with its own IP addresses. The key point for network policy is this: we don't target individual pods directly. We target them using labels. For example, we could have pods that have labels like app equal frontend or app equal backend. Network policies apply to all pods that match these labels. And let's move on to the services. Services provide stable access to pods. Because pods are temporary and their IPs can change. A service provides stable IP, stable DNS name, load balancing across pods. But the important note here is that network policies are applied to pods, not the services. Let's move to the next section and talk about default allow versus default deny. By default, Kubernetes allow all network traffic between pods. Front-end can talk to the backend, can talk to the database, and everything is allowed. This is called a default allow model. It is simple but not secure. Network policies allow us to move toward a default deny model, where only explicitly allowed communication is permitted. Now let's talk about ingress versus egress. Ingress means traffic coming into a pod. Egress means traffic leaving a pod. Same connection, two perspectives. For example, let's assume front-end sends a request to the backend. And here, this packet is egress. These network packets are egress for the front-end and ingress to the backend. This distinction is important because network policies can control each direction independently. Now, there is one more concept that often confuses people, and it's called stateful policy enforcement. Let's say we restrict ingress traffic to a pod using a default deny policy, for example, the backend pod. You might expect that if ingress is blocked, then response from external requests should also be blocked. But in practice, this is not what happens. For example, the backend pod can still reach external services like google.com. So the question is, why does this work if ingress is restricted? The answer is stateful policy enforcement. Most Kubernetes networking implementations, including Cilium, enforce network policies in a stateful way. This means the system tracks active connections and it understands who initiated the connection, which packets belong to that connection, which packets are request traffic, and which packets are response traffic. Let's walk through an example. The backend pod initiates an outbound request. Backend sends a request to the google.com. This connection is recorded as an active flow. When the response comes back, it actually automatically allowed because it belongs to an existing connection. So even if ingress traffic is restricted, return traffic is not dropped because it is not treated as a new connection. It is a part of a stateful flow. And without a stateful enforcement, every response packet would require a separate rule, which would make networking extremely complex. So in practice, we usually only define the direction that initiates the connection, and the system handles return traffic automatically. Now that we understand Kubernetes networking fundamentals and how the stateful enforcement works, we are ready to move on to the next sections. So now that we have learned about basic core concepts in the Kubernetes and some concepts about network policies, now let's move on to really write and apply network policies. So as I showed you before, we have two namespaces and they are dev and prod, and we have three pod in them called database, backend, and frontend. So let me just quickly show you these pods. Get pods dash and dev, and also we have the same pods here in the prod namespace. And also, as I said, we have web UI for these applications, and we can here see like this is the front-end application UI that we can send a request to the backend database in the same namespace or other namespaces, or even the internet endpoints like google.com or other APIs. And also these are the prod pods UI, web UI that I'm showing you now here. And let's just check that if front-end pod can send a request to the backend pod in the same namespace. And if I click here, as you can see, it sent the request and it was successful. Let me send one another request to the database on the 5432 port, and as you can see here, it was successful. And also let me just try to send a request from the front-end dev pod to the backend prod, I mean the prod namespace to the backend pod of the prod namespace. So let me try just backend and then the namespace. I think I should enter the namespace called prod. Would it be enough? Yes, as you see, it sent a request to the prod backend pod and it was successful. So let me show you here in the Hubble UI. We can here see that front-end pod. Let me click on it, and as you can see here, front-end pod can send a request to the database and backend on the listening port of the database and backend, and also the backend pod send a request to the front-end pod of the dev namespace, send a request to the backend pod of the prod namespace. and it's working fine because we haven't specified any network policies. So let's write and apply our first network policy. So here in this folder, in the network policies folder, I'm creating a new file. Let's call it 01 deny all.yaml file, and let's just copy the network policy that I've written, and it's so simple. Let me just review one line by line, and here we choose eBPF version of networking.ktest.io version 1, and the kind is network policy, and it's the default resource type called network policies, and we have namespace in metadata and the name for our network policies. And here in the spec section we have pod selector, and we define a curly bracket, and open and close curly bracket, and it means that it selects all the pod in the namespace that we define our network policies. And here we have policy types that it's a list that contains ingress and egress, and this policy, as I called deny policy, default deny, it's just deny all incoming and outgoing traffic. So let me save and kubectl apply to apply the policy, and yes, I applied the policy, and let's just see in action that we can send a request to the backend pods in the same namespace and other namespaces like prod. So let me check, and here actually, it's a good point here, because we applied default deny, so it contained the egress and egress, right? And that's because we can't access the web UI because we can't reach to the pod, and that's it. It's a great point, and keep this in this video, and it's so great that it happened, and I recorded for the learning purposes. But here in the prod namespace, as you can see, we don't applied any network policies for the prod namespace, and all connections and all requests are working fine. And here, if we can see, as I showed you here, it shows that it drops these requests that comes from the dev namespace for each pod. But let me just show you the prod namespace, and here, as you can see, all of them is working fine, except for the dev environment. If we send any request to the pods that in the dev namespace, it won't work, and you can see here. So as you can see here, we can access to the web UI of our pods, and we wanna fix this first. So let me go to the terminal, and here we have our first policy, But let me just write another policy and call it, I want to name it allow front-end ingress, because we want to allow all ingress traffic to the front-end pod. And the pod named front-end, and that means we should allow everyone to access the front-end. So let me just copy and paste the policy that I've written before. So here we named our policy allow front-end ingress, and it belongs to the dev namespace. Here in the spec section we choose the front-end pod with the match label, and under the match label we have app colon front-end, that it selects the front-end pod. And in the policy section we write the ingress policy type here, and in the ingress section we allow the traffic from each IP source. I mean, that's the thing that does with these 4 zeros, and the /0 means all of it means all IP addresses. So we save this file and let's just apply it with kubectl. Allow front-end ingress, and wait, takes too long. So it's created. Let me show you the web UI, and as you can see here, we can have access to the front-end pod's web UI, but we don't have access to the backend or the database web UI. And yes, so let's just move on to the next policy. We wanna allow front-end pod talk to the backend pod. So for this, let's create a file named front-end to backend .yaml file. Here, let me just copy and paste to speed up our process. Here, as you can see here, we named our policy allow front-end to backend in the namespace of dev, and in the pod selector we choose the backend, and in the policy types we choose the ingress, and in the ingress section we selected the front-end pod because we want to allow the traffic from backend to the front-end pod, and on the port 8081 with the TCP protocol. So let me just save and apply this policy with kubectl apply front-end to backend, and we apply the policy. So we should access to the backend pod, right? But let me just try. So now you can see that it couldn't reach out to the backend pod, and it couldn't resolve the DNS. And we should allow to the pod to talk to the core DNS in our cluster to resolve the actual IP of the pod. So for that, let me write another network policy that allows DNS we wanna our pods to be able as the core DNS and resolve the host names or the URIs. So let me write the rule here, the network policy I mean, and we name it allow DNS. I think it's a better name, allow DNS, and let me copy and paste. And here we named our policy allow DNS in the dev namespace. We select all pods because we want to apply this policy to all pods, and it makes all pods to access to the core DNS. And in the we choose the egress because pods ask the core DNS, and the they send requests to the core DNS. And here in the egress section, we select the namespace, and the core DNS is in the kube system namespace, and in the pod selector we choose the kube DNS. It's the label of the core DNS in our cluster. And in the port section we allowed the egress to send the request on the UDP and TCP on 53 port. Let me just save this file and apply it with the kubectl. And we apply the policy, and let me try again. And as you can see, it solves the DNS. But we have a problem. It solved the backend to the. It resolved the this host name, or call it the URL or whatever you want, and it can resolve this, but it couldn't talk and send the request completely successfully. So the problem is we didn't specify the egress for the front-end pod that it can send the request to the backend pod. So let me just add a rule here to make the front-end pod to talk to the backend pod. When front-end to backend, and let's add the egress here. Right, egress, I mean, it's not the best name, that let's name it this way for now. So now let's just copy and paste to speed up the process. And here I just named our policy allow frontend to backend egress in the dev namespace. And in the spec section I select the frontend pod, and the egress section we select the destination pod, and here it's the backend pod. And in the port section we allowed the 8081 on the TCP protocol. So let me just save it and apply it with the kubectl. Frontend to backend egress. Yes. And so let's just check it again. And here, and as you can see, we successfully send and receive the request and response. I mean, we send the request and get the response back. And great. So far in this video, we've been creating and applying network policy to control traffic between our applications. For example, we allowed the front end to communicate with the back end, restricted the outbound traffic, and allowed DNS requests so our applications could resolve domain names. But here's something you might not have noticed. Every policies we've created so far has been a standard Kubernetes network policy. If we look at the YAML file, you'll see something like this. Let me show it here. And this is one of the network policies that we've written to allow front-end traffic to the back-end on the 8081 port. But let's see the API version. We can see that it's networking ktest.io/v1 and the kind is network policy. And it's not a Cilium resource, right? It's a native Kubernetes resource. So if we're using Cilium as our CNI, why haven't we created a Cilium network policy yet? That's because Kubernetes and Cilium have different responsibility. Kubernetes provides the network policy API and it defines what a policy should look like. But Kubernetes doesn't actually enforce those policies. The job belongs to the CNI plugin. In our cluster, the CNI is Cilium. So every time we applied one of those Kubernetes network policies, Cilium translates that policy and enforce it on the network. If this cluster were using Calico instead of Cilium, we could use the exact same YAML and Calico would enforce it instead. And that's one of the nice things about the Kubernetes Network Policy API. It's portable, right? And you can move between different CNI plugins without rewriting your policies. So now you might wondering, if Kubernetes Network Policy already works, why does Cilium have its own resource called CiliumNetworkPolicy? The answer is simple. The standard network policy is intentionally limited. It focuses on layer 3 and layer 4 networking. In other words, it understands things like pods, namespaces, IP addresses, TCP and UDP ports. That's exactly what we've been using through this video. But what if we want something more specific? What if we want to allow only HTTP GET requests, or allow access only to the /health endpoint, or allow outbound traffic only to example.com? Unfortunately, the standard Kubernetes network policies can't do that. It doesn't understand HTTP requests or DNS names. It only understands network connections, and that's where Cilium starts to shine. Cilium extends the standard network policy model with a new resource called CiliumNetworkPolicy. By using it, we can create DNS-Aware Policies, write HTTP-aware rules, inspect gRPC traffic, work with Kafka protocol, and much more. We've built several of these policies later in this video. Now let's spend a minute to understand how Cilium enforces those policies. For standard layer 3 and layer 4 policies, Cilium uses eBPF. Without going too deep into the eBPF, here's the important part. Cilium loads small programs directly into the kernel in the Linux kernel. Whenever a packet enters or leaves a pod, those eBPF programs evaluate the policy immediately. If the traffic is allowed, it continues. If it isn't, the packet is dropped. Everything happens inside the kernel, which makes policy enforcement extremely fast. But layer 7 policies work a little differently. Imagine we create a policy that says only allow HTTP GET requests to the health endpoint. At this point, Cilium needs to inspect the HTTP request itself. The Linux kernel doesn't understand concepts like HTTP methods or URL paths. So instead of making the decision in the kernel, eBPF redirects that traffic to a node local Envoy proxy. Envoy understands application protocols like HTTP, gRPC, Kafka, and DNS. It inspects the request, applies the layer 7 policies, and then decides whether forward or block the traffic. So you can think of Cilium as having two enforcement paths for layer 3 and layer 4 policies. Everything stays inside the Linux kernel. For layer 7 policies, eBPF handles the traffic over to Envoy for deeper inspection. The nice thing is that all of this happening automatically. As users, we simply write the policies, right? Cilium figures out the best way to enforce it. That's it. Enough for theory, right? Now let's see what this looks like in action. Now that we have understand the difference between Kubernetes Network Policy and Cilium Network Policies, let's see it in action and see what Cilium adds in practice. As you know, one limitation of the standard Kubernetes Network Policy is that it doesn't understand domain names. For example, let's say our front-end application needs to access to GitHub's API. With a standard network policy, we could allow traffic to an IP address, but that's not ideal because cloud services often use multiple IP addresses and those IPs can change over time. So let's write network policy here and call it allow GitHub FQDN.yaml file, and here let me just copy and paste the policy that I've written before. Here is the network policy, and let's look at this API version and kind. As you can see here, it's Cilium IO v2 and the kind is Cilium Network Policy. And we choose the name, and it's for the dev namespace, and for the match labels we write the app column frontend to select the frontend pod. On the egress section, we have allowed the DNS queries on port 53. And UDP and TCP protocols, and the rule for the DNS is that we selected everything, so everything can be resolved with this rule. And here's the important part: two FQDNs means that we can allow with this rule to allow request to reach out endpoint or call it FQDN on the certain port that we have set it on 443 here on the TCP protocol for the api.github.com. Actually, we could have just write a star here, and this means it can resolve any subdomains of GitHub, but let's put it back. And here we just want to resolve and match the FQDN that is exactly api.github.com, and let's save it, and let's apply with the kubectl apply -f allow GitHub FQDN file, and here let me just delete the network policy because I wanna see it first that it doesn't allow to access the GitHub to the GitHub API. Let's write it here: https api.github.com, and let's connect. and as you can see here, the DNS resolved, but the TCP connection failed. So, and that's because we have allowed the DNS queries via the network policy of the Kubernetes, and that's why it's resolved the DNS. Let's just apply the policy that we have written, and it created the policy, and let's just try it again. We here said https api.github.com, and as you can see here, it connected and get the response successfully. But before we moving on, let's pause on one detail. If you look closely at the policy we just applied, you'll notice something. We're allowing DNS traffic to Cube DNS on port 53. But wait, didn't we already do this? Earlier we applied a standard Kubernetes network policy called allow DNS, and let me show it here, the policy that we applied before. Policy allow DNS. That policy already allows every pod in the namespace to send DNS traffic on port 53. So why are we writing what looks like the same rule again, this time inside our Cilium network policy? Actually, here's the reason. The first policy only controls whether the packet is allowed to leave the pod. It's a yes or no check at the packet level. Port 53 protocol UDP or TCP allowed or blocked. It doesn't look inside the packet. It doesn't know what domain name is being requested. It doesn't know what IP address comes back in the response. Now look at our FQDN's rules. This rule works differently. For Cilium to allow traffic to api.github.com, it first needs to know which IP address that name resolves to. And the only way Cilium can learn that is by watching the DNS query and the DNS response itself. Not just allowing them through, actually reading them. That's what this part of policy does. This tells Cilium, don't just permit this traffic, redirect it through your own DNS proxy and inspect it. That's the missing piece our native Kubernetes network policy could never provide. It has no concept of DNS proxying, it just filters packets. So even though our DNS traffic was already allowed, Cilium was never actually watching it. Adding this rule inside the Cilium network policy is what switching on that visibility. Once Cilium sees the query for api.github.com and sees the response, it builds an internal map between that domain and that IP. And that's exactly what the FQDN rule in the network policies, in the Cilium network policies needs in order to work at all. So to summarize this part, the Kubernetes network policy answers the question, is this DNS packet allowed to leave the pod? The DNS rule inside our Cilium network policies answer a completely different questions. Like, can Cilium see inside this DNS traffic so it can enforce FQDN based rules? Two rules, same ports, two very different jobs. Now let's look at another capability of Cilium network policy. So far, every policies we've written has been based on IP addresses, pods, namespaces, and ports. But applications don't communicate using ports alone. They communicate using HTTP requests mostly. Let me show my front-end pod web UI that we can reach out to the backend on 8081 port, and we can actually this is possible because we had Kubernetes network policy to allow front end talk to the back end on 8081 port. Let me show the network policies that we have applied in the previous sections. It called allow front end. It wasn't that. Let me find the rule. Front end to back end .yaml file, and that's it. This is the rule that it allows backend accept ingress traffic from frontend on 8081 port on the TCP protocol. But let's just try some other like URL and passes like API users, and let's and as you can see, it can connect, or like health, it can connect. And also let's just like private, I think I spelled the private wrong, but it doesn't matter. It can connect to all passes that we can provide here. It doesn't matter. But actually we wanna like restrict our front-end application just to only like API and like API users, or like just /health endpoint. We don't wanna like allow it on the private path, right? So let's just apply a rule for that. Let me try. Let me move to the Cilium Network Policy directory, and here we wanna apply another network policy, Cilium Network Policy. Let's call it allow not allow backend. Let me just think about the name. Let's call it HTTP policy, right? I think it's more meaningful. Policy .yaml file. Let me just copy the policies that I've written before. And here, as you can see here, we are using Cilium Network Policy. So as you can see here, we are using Cilium Network Policy. We called our policy Cilium Network Policy backend HTTP, and we applied in the dev namespace. We are choosing our backend pod, and the ingress section we allow just the front-end app to send request on the 8081 port for TCP protocol. And the important part in this policy is here in the rules section. We define the HTTP rule that allows the get method, or you can call it get verb, and it allows only the /health path and /API and .star. It means all thing possible here. I mean /API and everything you want put there. It allows these passes. So let me just save this rule, this policy, and apply it with the kubectl. Just wait seconds. Let's look at and test again. And as you can see, it showed allowed in the green light, but in the HTTP status, we can here see that it's getting 403 response, and that's working fine, and it gets access denied from the Cilium. So that's it. But also let me try to like get the health path, and as you can see we get 404, and that's totally fine. And also let's try do API and whatever want here, because we just set everything with a star dot and star, and it should return 404. But if we like API v1 here, put the v1 here, it should return the 403 response. Yeah, and that's working fine, and that's it for this demo. Also, I will update the web UI to kinda show the 403 status code with it's kind of confusing that it shows in a green light that it's allowed, but it should I can make it better, and I will update my repo. And also, before we moving on to the next part, let's show you the hubble. And as you can see here, let's just try to reach out to the API v2 again, like, or let's try something else, like a dummy path, and let's connect to it. And as you can see here, it gets the 403 status code, but let's see it in Hubble. And actually it didn't show it here. Let me just refresh. And it has some kind of delay, a little delay, and it just show it dropped. But let's just put a valid, not valid, allowed path that we specified in the network policy. Let's just call it valid, and let's just see it in Hubble if we get that forwarded. And as you can see here, it forwarded this request because it's allowed on this path that we specified before in the network policy that we've written. And that's it, I think. Let's look at one more policy, but this time we're not going to apply it. We're only going to explain it because it doesn't actually apply to our cluster. So let's call this policy like cluster wide YAML. And let me just copy and paste. First, notice something different here. This isn't Cilium Network Policy, it's Cilium Cluster Wide Network Policy. The difference is simple. A regular Cilium Network Policy lives inside a namespace and only affects pods in that namespace. A Cilium Cluster Wide Network Policy isn't tied to any namespaces. It applies across the entire namespace. I mean, the entire cluster. That's why the endpoint selector here is empty. An empty selector, like I said before, means match every single pod in every namespace. So whatever rule we write here applies cluster-wide, everywhere, all at once. Now let's talk about what this rule is actually doing. This is an explicit deny rule targeting one very specific IP address, 169.254, 169.254. If you worked with AWS, Google Cloud, or Azure before, this IP address might look familiar to you. It's the cloud metadata endpoint. On most cloud providers, every virtual machine can reach this specific IP address, and behind it, the cloud provider exposes internal information about this instance. Think like temporary credential, instance rule, startup scripts, sometimes even IAM permissions. This has become one of the most common attack paths in the cloud environment. If an attacker managed to trick an application into making a request on their behalf, for example through a vulnerability like server-side request forgery or CSRF, and that application happens to run inside a cloud VM, the attacker can point that request at 169.254, 169.254 IP address. and suddenly they might walk away with credentials that let them access far more than just that one application. That's why in almost every serious Kubernetes security setup running on AWS, GCP or Azure, you'll see a rule exactly like this one. A cluster-wide deny, blocking every pod in the cluster from ever reaching that address. Now here's why we're not applying it. Our cluster isn't running on AWS or Google Cloud or Azure. We set up this cluster up ourselves on self-managed servers using Kubernetes. There's no cloud provider underneath, which means that there's no cloud metadata service listening on 169.254, 169.254. So applying this policy on our cluster wouldn't really protect us from anything. That said, it's still important to know this pattern. If you ever deploy a cluster on a cloud provider, whether that's EKS, GKE, AKS, or anything similar, this is one of the very first policies you should consider adding it. A single cluster-wide rule, blocking every pod from ever reaching the metadata endpoint, regardless of namespace. So to summarize, this policy uses Cilium cluster-wide network policy instead of Cilium network policy, so it isn't limited to one namespace, it protects the whole cluster. It blocks access to 169.254, 169.254, the cloud metadata address. And in our case, since we're running on self-managed infrastructure with Kubernetes, this specific address isn't relevant, but the pattern itself is something you'll want to remember for any cloud-hosted cluster. So that's it for this video. I hope you enjoyed and learned something new from this video. I'll put all the links and resources in the description. And yeah, take care and have fun.